Greetings. We will continue with the quantum mechanics and symmetry of the hydrogen atom. The question that we began discussing is this, that how come the energy level of 3p and 3s, these energies are different, but for the hydrogen atom it is not the case, and this is the main question that we have begun to address in this. And we are going to discuss the operator for rotations, because the hydrogen atom has got a central field symmetry which is the 1 over r Coulomb field, and we recall that the generator for translations in homogeneous space is the momentum, which is given by the gradient operator here, and we need to find the appropriate operator for the angular momentum. So the linear momentum is given by the gradient operator, which is minus IH cross gradient, and we have to find what is the appropriate operator for the angular momentum. Now the angular momentum is the generator for rotations in isotropic space. Everybody knows what is meant by isotropy, right? Isos is same, tropy is different orientations, different directions. So no matter which direction you look at, conditions are exactly identical in isotropic space, and the physical idea behind the angular momentum operator in quantum mechanics is governed by two central ideas. One is quantization, of course, and the second is the symmetry that it connects to. And symmetry and conservation laws, they play an extremely important role in our understanding of physics, and I would like to draw your attention to these semi technical popular articles which I have been associated with. The first one with a student by name Shamala, and the second by my colleague, second is with my colleague Jim Libby, which who I believe all of you know, and these articles are available on my web page, so you are quite welcome to go through them at your convenience. And we focus on rotations. So you consider the rotation which takes a point from an original point to another point, and the new position vector is r subscript r, which is r plus delta r, and you can easily see that this infinitesimal displacement vector is given by the cross product of delta phi and r. Delta phi is an infinitesimal angle, okay, and that is a vector. Finite rotations are not vectors, but infinitesimal rotations are. So this is an infinitesimal rotation, and we have written the response to rotation of a point in 3-dimensional space, and you can write the new vector with Cartesian coordinates, which will be given by the coordinates of the vector r plus delta phi cross r. So it is a very straightforward thing to work out. You can also write this as a matrix relation, as an operator, as a matrix operator operating on the original position vector. So xyz is the original position matrix column vector, and if you operate on this by a matrix, or you pre-multiply by the matrix that you see, then the matrix multiplication rule will give you the new vector. So you can express this also as a matrix operation. Now the question before us is, how does a quantum mechanical wave function respond to rotations, or any function? Okay, our interest will be on quantum mechanical wave function of a system, but in general any function, no matter what it is, it may not have anything to do with quantum mechanics. How does a function respond to rotations? We have seen how the coordinates of a point respond to rotations. So the question is, how does a function of coordinate? R is now the argument of psi, and essentially what it means is that if you have a function with a certain contour, so let us consider some shapes, and they can be any kind of arbitrary shapes. Means you have two shapes on this in this figure. One you can describe as a square box with an arrow sticking out of it. There is some description which is possible, simple description. The other one is some arbitrary shape, and it can be absolutely any arbitrary shape. You can pick up a pebble from the sands at Adyar beach, and that is the shape you are talking about. Now the question is that under rotations, how does this function which describes the contours of this, how would it respond? So what you have in mind is obviously some process of this kind. Okay, so you have a figure and you have rotated it. So the meaning of rotation is very clear now. Now essentially what the rotation operator does, this is the rotation operator u. It operates on the original function phi psi and gives you a new function phi, and the reason it is rotation is because it changes the contours of the function on which it operates in such a way that the new function, it has got exactly the same value and amplitude at the new orientation as the old one, original one had at the original orientation. Okay, that's meant, that's what you mean by rotation. So there is no stretching, there is no compression, there is no deformation, right? It's a pure rotation, that's it. So this is the sense you have in mind. So now we ask the question, how do you express the new function phi in terms of the original function psi? If you can find a recipe to get this, you would know precisely what the rotation operator is. Okay, so you have to find out what kind of an operator will generate this transformation. So let us write that. So you have the rotation operator which operates on psi, it gives you a new function, and the reason there is no stretching, compression, deformation which is involved, it means that the new function will have such amplitudes at the new orientation as the original had at the old orientations. Okay, the only thing that has changed is the orientation, which is the rotation, which means that you can get phi completely equivalently, you can describe it as a function of psi, but with an argument which is transformed backward. Okay, so phi must be expressible as psi whose argument is r inverse of r, and now we almost have solved this. Okay, that is the connection. So rest of it is very simple algebra. So once you get this idea home, you know that this function whose argument is shifted by r inverse, this r inverse of r you know is psi of r minus delta r. So it is the value of the function at a neighboring point, and you know from differential calculus that if you know the value of a function at a certain point, you can always get the value of the function at a neighboring point if you know the rate at which it changes from one point to the other, right. The derivative is something that you need. So we will use that machinery, we can do it for arbitrary state vectors. So alpha is some arbitrary state vector in the Hilbert space, no matter what it is, and we are asking the same question, how does it respond to rotations? So what we do is to insert the unit operator. We have the resolution of unity, as you can see clearly, right, and now we operate on the eigenket r, which is an eigenket of the position vector, by this rotation operator, and we know that when this rotation operator operates on the eigenket of a position operator, it rotates it, shifts it to a new position which is r plus delta r. So this result is already known. So we plug it in, and now what do you have? You have integration over whole space of a vector scaled by this scalar, which is the position representation of the state vector alpha, right, and this is an integral over whole space, and the integration label is always a dummy label. So instead of r plus delta r, if you take r prime to be equal to r plus delta r, then the integration over r can be shifted to integration over r prime. But when you do that, every argument r must be replaced by corresponding r prime appropriately. The difference is delta r. So what it means is that this function r alpha, this one, right, this will be written as the position representation of alpha, but the argument will be r prime minus delta r. Is it clear, everybody? So I bring it to the top of the next slide here. Now you have got alpha at r prime minus delta r, and you know the connection between the Dirac representation and the Schrodinger-de Broglie function representation. Okay, psi alpha r is nothing but the coordinate representation of the state vector alpha. So when you have the argument r prime minus delta r, which is what you have in this integrand, right, in this integrand the argument is r prime minus delta r. So you are looking at the function psi at a coordinate r prime minus delta r. So this is like looking at the value of a function at a neighboring point, which is equal to the value of the function at the original point, and you have to add the difference coming from the displacement, but you have to take only the component of the gradient in that direction, right. So this is elementary first order differential calculus. So you plug in that result. The original function is psi alpha r prime, which you have written here. The second term is the component of the gradient along the displacement, and it will also depend on the size of the displacement. Okay. And now you can write this expression, insert these two terms in the integrand over here. So let us do that. We have these two terms inserted in the integrand, and now you have two integrals to work with. So let us see what they turn out to be. These are the two integrals at the top, in which delta r I recognize as the cross product of delta phi with r. We have already seen that. So we insert this equivalent term delta phi cross r over here, and here you see a scalar triple product. This is a triple product of delta phi r and del and the gradient of this function, right. And in a scalar triple product you can always interchange the dot and the cross. So now you have delta phi dot r cross the gradient of this function. Now what essentially it means is that since the gradient operator is nothing but the momentum operator, it is momentum divided by minus h cross, okay, you recognize that you have the cross product of r with p, and that is the angular momentum. So you get the angular momentum operator, and you have the projection of angular momentum along the infinitesimal displacement vector angle delta phi. This is a scalar product of two vectors. Delta phi is a vector as an infinitesimal rotation angle vector. So I have just expanded it in terms of the components of delta phi and j. Let us bring it to the top of the next slide here, and I now have an expression for the rotation operator, because the operator in this beautiful bracket, in this parenthesis, right, the operator in the beautiful bracket does to alpha what the rotation operator does to alpha. So it essentially gives you the exact form of the rotation operator, because in the integral you see that you have got a unit operator, you can insert it, you can take it off. So essentially what you are looking at is the rotation operator operating on alpha. So this gives you an exact identity of the rotation operator. The rotation operator, in as much as the linear momentum operator was expressed by minus IH cross gradient, the rotation operator is generated by the angular momentum. Rotations are generated by angular momentum, and that is what we have seen over here. So 1 minus I over h cross delta phi dot j, which is the operator sitting in that beautiful bracket, that is the rotation operator, and you can write it for different components depending on the rotations being about the x axis or the y axis or the z axis or about any arbitrary axis in space. You can always find the corresponding form. So you have these three components for jx, jy and jz, and if you just consider these rotations one after another, so you take any shape, it can be absolutely arbitrary shape, it can be this shape, it can be this bottle or whatever you want, right, and subject it to rotations about the x, y and z axis, rotate it about the z axis, do it like this, then rotate it about the x axis, okay, or do it in the reverse way, first about the x axis and then about the z axis, okay. Now you know how to do it. But what I did to exaggerate, to make a point, I showed you finite rotation through 90 degrees, okay. I showed you a rotation through 90 degrees like this and another 90 degrees rotation like this. Now do not do that, do these rotations through infinitesimal angles, but do exactly the same. First a rotation about a z axis of an arbitrary shape, it could be this bottle, it could be a piece of stone, it could be anything, okay, and do this exercise. You have to draw these diagrams in your notebook, take some arbitrary shape, subject it to a rotation about the z axis through an infinitesimal angle, not a finite angle, okay, about the z axis, then do the same about the x axis and then carry out the rotation, the same two rotations but in the reverse order. What you will find that the result of these two in the reverse order will give you the rotation about the third axis. Just do this, you have to actually carry out, draw these pictures in your notebook. This is in fact a problem from Schiff's quantum mechanics, okay. And when you do that, you will find that these rotations really do not commute, they do not give you the same result. Linear displacements, they commute, px commutes with py, but jx does not commute with jy. So the group of the displacement operators is abelian, the one for rotations is not abelian, it is non-abelian, and essentially what you find is that the commutation relations for angular momentum automatically come out of this property that rotations about orthogonal axis through infinitesimal angles do not commute, okay, you get a different result. So these are the commutation relations that you get for angular momentum, and you accept these to define angular momentum. This is now the definition of angular momentum. We are not going to refer anymore to r cross p, okay, we have used that idea, all right. Nevertheless, we are not ever going to refer to angular momentum to r cross p. Our definition of angular momentum now is the following, that angular momentum is such an operator in quantum mechanics, it is a vector operator in quantum mechanics whose components follow the commutation rules which are in front of us, that jx comma jy is equal to ih cross jz and corresponding relations for jy jz and jz jx. This is the definition. There are other equivalent definitions, that the cross product of this operator with itself does not vanish. This is a completely non-classical result. In classical, if you were dealing with a classical vector, the cross product of any two collinear vectors, let alone itself, would vanish, right, but angular momentum is a peculiar one, and this definition is a completely equivalent definition to the commutation rules definitions. You can get one from the other and vice versa. You can also define it through this commutator, that the commutator of j with j is equal to I h cross j. If a classical operator would always operate, will always commute with any other operator which is proportional to the rotational one, right. A comma any constant multiplied by the operator a would vanish. That does not happen with the angular momentum. And all of these three definitions, the commutator definition, the cross product definition, or the commutation of the components, these are all completely equivalent. You can get one from the other. It is just a matter of doing some algebra to get one from the other. These are all equivalent definitions of angular momentum in quantum mechanics, and essentially one must remember that there are three attributes of angular momentum that you must carry. One is that it is a quantum creature, second that it is a vector, and third that it is an operator. So all the three attributes, that it is a quantum operator, it is a vector operator, and that it is essentially an operator, and therefore it will meet the requirements of the operator algebra. It will operate on appropriate operands, giving you new operands and so on, right, giving you new vectors. So all that algebra of operators has to be invoked when you work with this. So we now have defined angular momentum in quantum mechanics. Again, it would be a matter of straightforward algebra to show that the commutator of j square would commute with any one component of the angular momentum, but not with the other, with any other. Okay. So it could commute with jx, it could also commute with jy or with jz. It does not matter what you call as x, y, z. I can always choose a Cartesian coordinate system in which the z axis is pointing toward the zenith, toward the heaven, but you can point it toward the hell or east or west or any direction, it does not matter, any one direction in space. And therefore they have simultaneous eigenstates. And what we discussed in our first lecture in our previous class was that in quantum mechanics you are looking for a complete description of the state. You are looking for as many observations, as many measurements that you can carry out, so that you can describe the state completely. But the fundamental constraint is that the measurements have to be compatible with each other. They must be compatible with each other. So here you have compatible operators because they commute with each other. So you can carry out these measurements simultaneously, and you can get that much information at the same time. So when you are looking for information about the hydrogen atom, you can then get simultaneous information about j square as well as ju along any given direction, it does not matter what. So you can develop the eigenvalue equations. You have the eigenvalue of j square, you have the eigenvalue of one component, it could be jz, it is any unit vector u, it could be z or x or y or whatever, and since it is a simultaneous eigenket of two operators which commute with each other, there are two good quantum numbers which come out of it. One is j, the other is m. Okay. So these two quantum numbers will now describe the hydrogen atom, and from the algebra of angular momentum, and some of it we will discuss separately, it will turn out that the eigenvalues j can take any value which is either 0 or half or 3/2 or 2 and so on, any half or integers, half odd integer or integers. The corresponding value of m will go from minus j to plus j. So these are the possibilities. Now this angular momentum, it could be the orbital angular momentum, it could be the spin angular momentum, it could be the total angular momentum, or it could be the resultant angular momentum coming from the addition of a large number of sources of angular momentum. So, whatever be the source of angular momentum, it will all integrate to give you a net angular momentum, and in every case if it is to be an angular momentum at all, then it must meet the defining criteria of what an angular momentum is. So, now our first consideration is reserved for the orbital angular momentum of the hydrogen atom, which is L square. L will go in this case from 0 to any number that you can think of, all integer numbers. Half integers will not appear in this. When you are dealing with the orbital angular momentum, you will never have half integer quantum numbers. They come from a different source of angular momentum, which is the spin. So, spin will contribute half integer quantum numbers, but not orbital angular momentum. And both spin as well as orbital angular momentum will satisfy the defining criteria of angular momentum, which are these three equivalent definitions of angular momentum. Now, very often when you think of spin, these pictures come to your mind. Okay? This is something that you cannot avoid, because spin is something that you always think about. These are the pictures that come to your mind, and that is very unfortunate, because that is not what spin is. Okay, if you see any of these pictures associated with the spin angular momentum, these are absolutely wrong, and there will be 3 devils, 3 skulls coming after you, 3 ghosts, minimum 3 ghosts. So, be aware. So, do not use these pictures whenever you talk about electron spin. I am sure you recognize the skulls whose they are, do not you? One might be Pauli. Who are the other 2? I do not know which one is Pauli. So, there is no classical analog to spin, absolutely none. It is a quantum creature. There is no classical analog, it comes straight out of quantum mechanics. So, you talk about spin angular momentum, which has got nothing to do with spin in the conventional sense. You also talk about orbital angular momentum, which is absolutely nothing to do with orbits. So, orbit also does not exist. We already discussed it. For an orbit to exist, an orbit is defined in classical mechanics. It is the trajectory in phase space of a point which is described by position and momentum, but these two cannot be simultaneously measured, and therefore orbits do not exist. So, orbital angular momentum has nothing to do with orbits, spin angular momentum has nothing to do with spin. What is it then? So, first we have said what it is not, but we have also said what it is. Now, what it is that it is a quantum vector operator whose properties are such that j cross j is equal to I h cross j, that jx comma jy is equal to I h cross jz. So, these are the defining criteria of angular momentum. So, in fact, when spin was introduced by Uhlenbeck and Gaudsmit, it worked, but they did not know why it worked. So, in fact, Uhlenbeck called it as abracadabra, that it is something like magic which seems to work, but the actual definition is just completely mathematical. It works, but then it connects to observations, it connects to observables, but to see these connections you have to develop the algebra further, as Dirac tells us in his book. Okay. So, these are mathematical definitions. Now, we are working with rotations over here, and a rotation matrix you can write with these 9 components. It is a 3 by 3 matrix, but then there are 6 constraints. So, there really are 3 independent parameters, which are the Euler angles, if you might consider. Okay. These 3 parameters can be changed continuously to describe different rotations. So, one rotation differs from the other rotation by an infinitesimal change in these parameters, and because these changes can be brought about infinitesimally, there are infinite number of these rotations. So you can stack them all together and they form what you call as a rotation group. Everybody knows what a group is. Okay. So all the rotation operators, you stack them in a set which is a mathematical group. So you have the existence of an inverse, existence of identity, you have got a binary operation that is defined which gives you the new element. Okay. There is a closure property and so on. So these are, you go from one to the next by variation of some parameter. It could be the Euler angle, and these changes can be absolutely infinitesimal, and you have the rotation group defined by this. Now this plays a very important role in the quantum mechanics of the hydrogen atom. Now typically when you go from one position vector to another, we agreed that you can represent it by a matrix operation, and if all this has done is to preserve its norm, then the determinant of the matrix R would be either +1 or -1, and you have a choice. You can think of the +1 matrices as well as the -1 matrices. Okay, the one which has got a determinant which is +1, or the one that has got determinant which is -1. And it is important to remember that in rotations you are dealing with these orthogonal matrices in which the transpose is equal to the inverse. Okay, so you always have operations of this kind, but then you take a subset of those matrices whose determinant is +1 and not -1. Now this is extremely important. So you are dealing with orthogonal matrices, but not all kinds of orthogonal matrices, special orthogonal matrices. What is the specialty? That these are such orthogonal matrices whose determinants are +1, those with -1 are removed from your consideration. So that is what makes it SO. Okay, S for special, O for orthogonal, and then you have got the group is called SO3 because the number that appears in the parentheses, it is connected with the number of generators, and I will tell you what that relationship is. But these are special cases, or some examples of Lie groups, and you exclude those with negative determinants. Okay, you are dealing with those determinants which are positive. So this is named after Sophus Lie, and this would distinguish it from reflections, because when you look at a reflection, you always see that right goes to left and left goes to right, but you do not see the top going to the bottom and bottom going to the top. It is the same symmetry in a certain sense, right? And the reason this does not happen, and I have heard all kinds of answers when I raise this question, means you begin to think about laws of reflection, angle of incidence is equal to angle of reflection and so on, and all those answers are not correct. The real reason is the following, that when right goes to left and left goes to right, you have got a vector xyz which goes to -xyz, for example, right, and what you have is the operation is described by a matrix whose determinant is -1. Okay, this is what happens in reflection. So this is an operator which is represented by a matrix whose determinant is -1, so it will not come in our consideration for rotations. Okay, that is what distinguishes reflections from rotations. The top would go to the bottom and bottom will go to the top. It is just a matter of what is the plane of reflection. Okay, but then again the matrix will have a determinant whose value is -1, as you can see. Okay, in rotations you will always have a matrix whose determinant is +1. So the reason top does not go to the bottom and bottom to the top, same time that right goes to left and left goes to right, is because the matrix is different. So, it is a different kind of operation. It is a symmetry operation, but it is a different symmetry. It is a reflection symmetry. This one is a rotation symmetry. So, this group which describes the hydrogen atom, it is called as the SO3. The number 3 actually comes from, it is generic. There are a family of groups called SON. It could be SO3, SO4 and so on, where the argument of SO gives you the number of generators by the relation n into n minus 1 by 2. So, when n is equal to 3, 3 into 2 by 2 gives you 3, and there are 3 generators for the rotation in Euclidean space, which are the 3 components of the angular momentum. So, they constitute the SO3 group, and the symmetry of the hydrogen atom is described by the SO3 group. But as we are going to learn in the next few classes, there is more to this. So, this is our elementary introduction to the symmetry of the hydrogen atom, that this is described by the SO3 group. We know that J square can be measured along with one more component. So, you can get information about 3 different characteristics of the hydrogen atom, right. You want to describe the hydrogen atom. The reason you are doing quantum mechanics of the hydrogen atom is just that you are looking for a quantum mechanical description of the state of the hydrogen atom, and the state of the hydrogen atom is described by a state vector, which is to be labeled appropriately. What are the designations? The designations will come from those measurements that you can carry out, and you will look for a complete set of compatible measurements. And you have learned that the compatible measurements for the hydrogen atom are J square and Jz, or J square and Ju, where U is any unit vector in some space. So, these two will give you some information about hydrogen atom, and they both commute with the Hamiltonian, which describes the energy of the state, because energy is conserved if you have an isolated hydrogen atom. As time progresses from today to tomorrow to day after, left to itself, energy is conserved. So, you can always measure energy. Okay. So, energy is conserved, and these 3, the energy operator, which is a Hamiltonian, the angular momentum operator, which is L square, and one of its components, which is Lz, these 3 will give you a complete set of compatible observables. The eigenvalues of these operators will give you a complete description of a state vector. That is the reason you characterize the state of the hydrogen atom as psi n L m. N comes from the eigenvalue of the Hamiltonian, L comes from the eigenvalue of L square, and m from the eigenvalue of Lz, because these 3 operators commute with each other. They correspond to measurements which can be carried out simultaneously, and these 3 together will describe the state of the hydrogen atom completely. They are therefore called as good quantum numbers. Okay. This is what you mean by a good quantum number in quantum mechanics. Okay. Quantum mechanics, you have numbers which have their virtues and vices. These are good quantum numbers because you can carry out corresponding measurements. These measurements are compatible with each other. The first one, of course, is the energy, and you are basically asking the question, what is it that you can measure? So, since energy is conserved as time progresses, and the example that I like to give is this hero whose energy seems to be conserved no matter what happens. Yeah, and energy, of course, gives you one quantum number, which is the energy label, which comes from the eigenvalue of the Hamiltonian, but then you also get the eigenvalues of J square and Ju. So, n, L and m. So, these are the 3 quantum numbers that we have for the hydrogen atom. So, I am going to take some questions now. and on any of the two classes that we have had. So rest of it is straightforward algebra. The basic moral of the story is that you seek as much information as you can, but the rider is that you cannot seek whatever information that you want to seek. That if you say that I want to know the position of this object, I also want to know the momentum, and I ask these two questions. And this is something which Niels Bohr summarized very nicely when he said that quantum mechanics will not give you all the answers, but quantum mechanics will tell you what are the right questions to be asked. Okay? So it is not quite a right question to be asked to say that I want to know what is its exact position, I want to know what is its exact momentum. Nothing wrong in asking this question, means if you were not aware of quantum mechanics, but once you learn quantum mechanics, you learn what are the right questions to be asked. You have come to terms with the fact that certain measurements are compatible, some measurements are not compatible. So obviously what you do is to stack all the measurements which are compatible, and for the hydrogen atom the measurements which are compatible with each other are the energy, the angular momentum which is J square, and one of its components. Of course, we all know that there are 4 quantum numbers, the 4th one will come from relativistic quantum mechanics. It has no place as such in non-relativistic quantum mechanics. So we will of course introduce that, which is the spin. But in non-relativistic quantum mechanics you have n, l and m. N I am using tentatively because it only represents the energy quantum number for discrete states, but you also have energy of continuum states, in which case the quantum number is not n, but it is still an energy label. So we will discuss this in some further details, but tentatively I will use it. So thank you all very much. Any question?
So that j cross j equals ij and j comma j equals ij.
Yeah.
Okay, can you say something more about that? Because
yeah, essentially it is a quantum feature.
what I am saying is that j is not compatible with itself, which means j and j cannot have complete set of simultaneous eigenstates.
Well, what it means is that you cannot get information about all the components of j. Let me give you a very nice example here. Now you know that magnetic moment is proportional to the angular momentum. Okay? So if you have a bar magnet, and let us say this is a bar magnet, and you suspend it with a string or something, it will orient itself along the earth's axis, and you can say that this is the z axis. Now you ask a question, what is the magnetic moment of this bar magnet, and you will come up with some value for mz, and mx and my will be 0. Okay, because this bar magnet, if it were a classical bar magnet, will orient itself exactly along the z axis. Okay. Now quantum bar magnet, and nature is quantum mechanical. So whatever we talked about this bar magnet in classical terms was only an approximate description of a magnet. Real magnets will have to be quantum mechanical. Okay. And a real magnet cannot orient itself like this. The reason is, if it were to do that, you would then know all the 3 components of the magnetic moment exactly, that the z component is mz, mx is 0, my is 0, you get all the 3. And since angular momentum is proportional to the magnetic moment, you would get jx, jy and jz exactly. That you cannot do, which means that a quantum magnet cannot be oriented exactly like this. And when you say that j does not commute with j, is essentially this, that you cannot get all the 3 components. So the physical information in the commutation of jx comma jy equal to I h cross jz, or j comma j is equal to I h cross j, is essentially the same, which is why they are mathematically equivalent. You can get one from the other, and the physical information is this, that if you want to measure all the three components, then it is not appropriate to ask the question as to what are the values of all the three components, and I want to know them simultaneously, because simultaneous measurement of these three components is not compatible with each other. For linear momentum there is no problem. Px commutes with Py, Py commutes with Pz, Pz commutes with Px, that is not a problem. Angular momentum, it does not happen, and that is not just a property of angular momentum, it is in fact the defining criterion of angular momentum. This property is precisely what defines angular momentum in quantum mechanics. It is a mathematical property, but then it connects to physical observations, and that is important. So it is not going to stay at that level, because our interest as physicists is in connecting it to observations. At the end of the day you want to do an experiment and connect it to what, to the theory that you are developing, okay, and that is going to happen when you develop the algebra further.
How do I actually show it that j comma j is equal to I?
That is just plain algebra, just work it out. It will take you 5 minutes to do it. Begin now and in 5 minutes you will see it. Write j comma j equal to jx ex plus jy ey plus jz ez comma jx ex plus jy ey plus jz ez. Take it term by term. You will find that you have to work with jx comma jy,
and then I will use those commutation relations.
Exactly, right, and when you put it all together the answer will turn out to be IH cross j. Okay, all right, good. Any other question? Yes.
Sir, you said that spin do not have any like physical analog. So how does it respond to the magnetic fields when in Stern-Gerlach experiment when we try to observe the magnetic field?
Because there is a magnetic moment associated with angular momentum. So magnetism is a property which is not defined in terms of having a dipole of this kind, okay. Magnetic moment is something which responds to magnetic fields, and how does it respond? The reason it responds is because when you keep a magnet having a certain magnetic moment in a magnetic field, there is a certain energy which is given by this mu dot b term, and it is this which will orient it in a certain direction. But this is precisely why a quantum magnet does not orient itself exactly like this, and then in some of the models of old quantum theory it is suggested as if you have got an axis and this magnetic moment vector precesses about this. The precision conveys the idea that at any instant of time you do not have its components along the horizontal plane, but this is really the old quantum theory. But in formal quantum theory you have to describe it completely in terms of the components of the angular momentum and their commutation rules, and that will give you exact answers. And when you do the algebra, develop it further, get the expectation values, average values, then you will be able to connect them to observations, okay. So those are the observables, and these observables have to be defined through the expectation values, transition probabilities, and so on. That is very nicely said by Dirac when he says that when you develop the algebra further you can connect it to observations. So you do not have to invoke a wrong model even if you get some satisfactory answer, okay. So thank you all very much.